Alright, in this video we're going to introduce some concepts from beginning calculus. We're going to look at finding limits, both numerically and graphically. So the goal of this video is to really understand the limit notation and the concepts behind limits, because they are very, very fundamental to understanding calculus. So calculus is the next big step in mathematics. When you went from elementary school math, the arithmetic, to algebra, and you started introducing variables and unknowns, that's a big step. Calculus is like that, but going from ideas in algebra and trigonometry into limits and derivatives and integrals. So our goal in this video is going to be to really get a good understanding of limit notation and what limits are. So we're going to use a sequence to introduce these. So as we increase the term numbers of a sequence, so let's say we have a sequence where each new term is half the previous term. So it's a geometric sequence with a common ratio of a half. So we'll start with 1, half of 1 is a half of a half is a quarter, half of a quarter is an eighth, half of an eighth is a 16th, yada, 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 yada. And if we look at the values themselves are going to get closer and closer to 0. So we have 1 divided by a really big number down the road is going to be really close to 0. And then the next term after that is going to be even closer to 0 than the one before it. So as we progress with these terms, each new term is getting closer and closer and closer to 0. So the important thing to remember with limits, and I cannot stress this enough, that it may or may not equal 0 at some point. In our sequence it won't, but we say that the limit of the sequence would be 0. So whether or not it actually equals that value, the limits don't care about that. They just care what happens as we get closer and closer. So like sequences, functions can also have limits, and you'll be studying quite a bit of them in calculus. So to indicate the limit L of a function, f of x, as x approaches some value of a, we use the following notation, that the limit as x approaches a of f of x is equal to whatever that limit value is. Like our sequence limit, this would be a 0 here. So we read this again as the limit of f of x as x approaches a is L, or the limit as x approaches a of f of x is L. So as far as notation goes, to translate that into everyday language, it's either this here, the limit of f of x as x approaches a is L, or the limit as x approaches a of f of x is L. So in other words, as x gets closer to the x coordinate of a, the y values are going to get closer and closer to your limit value of L. So as our x coordinates get closer and closer to this value of a, our y coordinates are going to get closer and closer to this value of L. So sometimes you can just plug the value of a into the function and everything's well and good. Other times you cannot, so you might get division by 0, which we're never allowed to have. So this is, again, the most important concept in dealing with limits, is they only look at what happens as you get closer to that value of a. As the x values, the x coordinates get closer to that value of a. They are not at all concerned. The limit is not concerned at all with the value of the function at that value of a. So when you can plug in the value into the function and get a result in return, that's great. Limits do not care one bit about that. So please, above all other things, keep this in mind. Limits only care about what happens as the x coordinates get closer and closer and closer to the value of a. What are the output values getting closer and closer to? Or what are the y coordinates getting closer and closer to? That is the fundamental idea of a limit. Alright, so that about does it for this video. In the next video, we'll take a look at finding limits using tables. So I'll see you then.